let's have a look at the addition of graphs. And you've probably seen this before. You've probably seen it in science as well. I think they call it, what do they call it in science? Superpositioning of graphs. Does that sound familiar? Yeah? So if you want to add two functions together, basically, so the simplest way of doing it is draw them separately and then physically add the y values together, or get a ruler and measure, and oh look, that one's 1 centimetre, that one's 2 centimetres, so I'll plot 3 centimetres, that sort of thing. So if I wanted to draw x squared plus x, let's do a really basic one here. So there's y equals x squared, and there's y equals x. So key things to look for, x and y intercepts. Well, obviously the origin's going to be 1 because 0 plus 0 is 0. So we'll mark that in. Any other x-intercepts there? The other x-intercept would be, and I don't know how you do it with these ones, but I'd get a ruler and slide it sort of along, and when it's the same above as below, then you know, right, that's going to be an x-intercept as well. So roughly about there, I reckon, on mine. Then, now whether you physically draw them or, as I say, just slide a ruler along and just read off your ruler, but draw as many as you need. There's one. That one there's key. I'd certainly always go for the point of intersection, because you know it's going to be double that value if you're adding those together. That's a certain one. But look, as many as you need. There you go. Let's draw them in everywhere. I might have gone overboard. But anyway, and just add the y coordinates together until you've got an idea what the shape is. And I think I've got a pretty good idea there that I'm going to end up with another parabola. And voila, that would be our parabola, x squared plus x. Okay, let's try this one. X plus 1 on x. So a little bit more interesting. There's y equals x again, but now I'll draw in the hyperbola as well. Well, there's not going to be any y-intercepts, of course, because if it's not in the domain of one of the functions we're adding, it can't magically come into the domain of what we're adding together. So we know there's still going to be an asymptote at the y-axis. I don't know that we're going to get any x-intercepts, are we? Because on the right-hand side, we've always got positive plus a positive. On the left-hand side, we've got negative plus a negative. So I don't think we'll end up with any x-intercepts for this one. It's all right. I'll plot some points. There's a point of intersection. That's a logical one to do. So twice that value. And there's another point of intersection there. As I say, just plot as many as you need. And turns out y equals x is an asymptote. That has to be if you think about it, because we're adding 1 on x to it, and we know 1 on x can never equal 0, so therefore we'll never get y equals x. So it makes sense that y equals x ends up being our asymptote. And there's our new curve. So things to keep in mind, as I mentioned before, discontinuities. So any exclusions in the domain of the original functions will be a discontinuity in the new function. So this brings up a really interesting one. Say I wanted to add these two together. X plus 1 on x is one function, and 1 minus 1 on x is another function. Now, if I was to add those together, it looks like I'm going to draw the line y equals x plus 1. But we've got to remember about the discontinuities, because we're not drawing x plus 1. We're drawing these two graphs added together, and x equals 0 is not in the domain of those graphs, so it can't be in the domain of our answer. So yes, we get y equals x plus 1, but we have a point discontinuity at x equals 0, because that can't be in the domain of our new function. That's what I was talking about, finding the x-intercepts. So when the amount above is the same as the amount below, the positive and the negative will cancel each other. So that's how we can discover the x-intercept. Symmetry. So when you're adding, like functions will retain the symmetry. So what do I mean by that? An even function plus an even function will be an even function. An odd function plus an odd function, and that's what we've done there with x plus 1 on x. That's an odd function plus an odd function. The answer is still an odd function. So that new one still has that rotational symmetry there. Now, if you've got odd plus even, then you're going to lose the symmetry. But like ones will retain it. Absolute value of x plus 3 plus the absolute value of 1 minus x. When I do these ones, I like to look at the critical points. And the critical points for this is where the absolute values would be 0. So I've got -3 in the first one, and I've got 1 in the second one. And so I look at it and say, well, okay, when it's less than or equal to -3, what's going to happen? Well, if I was to pick a number less than -3, the absolute value of x plus 3 would be the negative answer. To give me a number that's less than -3. -4, okay. Sub -4 in, you get the absolute value of -1. So the answer is not -1, it's the negative of that. So for x is less than or equal to -3, I want the negative of x plus 3. Then we do the same one with 1 minus x. Would that end up being positive or negative? So let's use the same number, -4. 1 minus -4 is +5. So that one's okay. It'll stay at 1 minus x. Add them together. So for all the x values less than or equal to -3, I'm going to draw the line -2x minus 2. Now let's have a look in between -3 and 1. I think the easiest number to use there is going to be 0. If I look at the first one, 0 plus 3, well, that gives me a positive number. So it will stay as x plus 3. The second one, 1 minus 0, well, that's 1. So it stays as 1 minus x. Add those together. So in between -3 and 1, I'm just going to draw the line y equals 4. Well, what happens now on the right-hand side? A number bigger than 1. Go on, give me a number bigger than 1. Oh, so creative. Okay, 2. Put it in the first one. 2 plus 3 is 5. That's positive. So it's going to stay as x plus 3. Put it into the second one. 1 minus 2 is -1. So it's negative. So it's going to be minus 1 minus x. Add those together and I get the line y equals 2x plus 2. Now I can draw the graph. Up to -3, I'm drawing the line y equals minus 2x minus 2. So it would stop at the point -3, 4. Then it's going horizontal, y equals 4, until I get to the point 1, 4. And then after that, it becomes 2x plus 2. So we get this interesting, well, I don't know that you could call it a U, but interesting sort of shape there for that graph. If you had to draw function x minus g of x instead of plus, personally I always do adding. So the two things I would add would be the graph y equals function x, but y equals the negative of gx. And then I can just use the same technique. I just add those two graphs together. Now, the graph of y equals x plus gx, where gx has a bound. So the example I've used here is sine x. I know sine x always travels between -1 and 1, so it's got boundaries that it exists in. That means when I, well, subtract in this case, it's going to be bounded by x plus 1 and x minus 1. So the boundaries of the sine curve. But anyway, let's have a look at this one. We're going to have, well, an x-intercept at the origin. The other good ones to plot here, any x-intercept of my blue curve has got to be on my red curve, because I'm saying, so I will subtract 0. So it's staying there. So I know those points are still in there. Some other key points, the turning points are usually good ones. So I'll slide my ruler along and I get those points. And I keep doing that. What we'll end up with, it's not actually a sine curve. We're still going to get something that sort of winds along the line, but notice how it's not actually symmetric between those 2 points. Interesting shape. But as I say, if I was to draw in, and I wish I had now, but would have been a good idea. If I was to draw in y equals x plus 1 and y equals x minus 1, we'd see how that curve stays in between those 2 boundaries as it's winding along winding along the line y equals x. Alright, so adding and subtracting, let's have a look at multiplication. So I'm going to draw function x times g of x. Once again, we can draw the 2 graphs separately. And things to notice, now the example I'm doing down here is x times e to the power of x. I'm going to multiply those 2 together. X-intercepts, they're important because that's where the function is going to change sign. But I'm multiplying this time. So anytime one of the functions has an x-intercept, I must end up with an x-intercept because we'd be going 0 times the other one. So for here, the only one we're going to have is at the origin, because y equals x is equal to 0 there. So when I multiply it by the exponential, I'll get 0. But it doesn't look like there'll be any other x-intercepts for this one. Now, what we can do is just work out which region we're in. So the x-intercepts are going to break it up into boundaries. In this case, I've only got 2 boundaries. And I have a look at it and I say, well, e to the x is positive, y equals x is negative. So if I multiply these two things together, I must end up with a negative number. So I know I'll be down there somewhere. Then when I go past the origin, they're both positive. So I must be up there somewhere. So it gives me an idea of where the curve is travelling. Y-intercept, well, we've already got that. We know it's at the origin. Now, y equals 1 is a really important point. Because if you're multiplying it by the other curve, you're multiplying by 1, and so that y value will stay the same. So on mine, okay, so let's say that's where x equals 1, so obviously y equals 1 as well. I'd be multiplying my e to the x curve by 1, so I must end up on e to the x curve at that value. And then I could do a similar thing with negative 1. Over here at negative 1, I'd be multiplying, although I won't end up on this curve because it's the negative of it, but it'll reflect and be below. So there's a couple more points that I know. If one or the other of the functions approach 0 or infinity, so will the new function. And when you've got 2, because have a look at this on the left-hand side, the exponential is approaching 0, but y equals x is approaching infinity. So what's it going to approach? You've got 0 times infinity. Well, what on earth is that? This is where an idea called dominance comes in. The one that will dominate is the curve that gets the steepest, the quickest. So out of the exponential and y equals x, which one gets steeper, quicker? So it will dominate. So whatever the exponential is doing out at infinity, that's what this one will do. So when we've got that conflict, you have a look at the one that dominates, and that's where it will go. So it ends up looking something like that. Okay? So because I know the exponential is dominating, it's got to go towards 0. So when it comes through the origin, it must at some point turn and then come back so it can go asymptotic to the asymptote. Whereas over here on the right-hand side, well, they're both going towards infinity, but I've got it going pretty quick because, again, the exponential is going to dominate how quick it goes up. So things to keep in mind. Discontinuity, so once again, if we have an exclusion, or we didn't in this case, but if we had an exclusion, then it would remain. And symmetry, again, you'll retain symmetry. Here, it wasn't an issue. Y equals x, we got symmetry, but the exponential doesn't have symmetry about it. But it will retain when you multiply symmetry. Let's have a look. We've done ones like this before with polynomials. Here's just another way of thinking about it. If I'm multiplying these 3 curves together, so let's locate the x-intercepts, and the x-intercepts must be where each of these individual curves hit 0. That's going to break it up into sections. So starting at the left, I've got positive times negative times negative. Well, that'll be positive. Then in between these two, positive times negative, that's negative. Positive times negative, well, that's also negative. Well, that tells me something about the origin straight away. Must be a turning point there because it's got to come up, touch it and go back down. And then on the right-hand side, positive times positive. I've drawn it in there. Unfortunately, the scale of mine, it makes it look like, let me get rid of those so you can see it. So it's this greeny one. The scale of mine makes it look like I'm just going straight across, but it's just the very small y values. It actually comes down a bit and then comes back up to 1. So not just one function times another. What happens if we square a graph? So multiply it by itself. Single roots will become double roots. Any single root will become a double root. Here's my random graph from the other day. Let's use this one again. So there's function x, we're going to square it. These single roots, and we know they're single roots because they're cutting like a straight line, they will become double roots. So they're still x-intercepts, but they now will become turning points rather than cutting through. Any stationary point will still be a stationary point. The y value may change, but at that particular x value. So here, this stationary point here, at that x value, well, the y value is going to square. Now it's above 1, so it'll end up going higher, whatever that one is. So up there somewhere. Got to be careful with these ones because if we're squaring, it's going to go positive. So yes, this one, well hang on, negative one's down here. So when I square this one, it should become a smaller number, but it'll be on the other side of the x-axis now because it's going to be positive. So what do we know? We know we've got a turning point. We know it's up here. That's also going to turn. It's going to turn, turn, turn. What about this horizontal asymptote? Discontinuity is going to stay the same, but the horizontal and oblique asymptotes, square them. I mean, that's what we're doing in the function. We're squaring everything. So at the moment, I've got, well, it equals some constant number. So that's nice. I don't know, what is it, about a half maybe? Square a half, you'd get, so it's going to come down. The horizontal asymptote. If, and I'm just talking the magnitude here, that's why I put the absolute value. But if the magnitude of the curve is bigger than 1, then function x squared should be bigger than function x. So when you're drawing it, the new curve should be above the old curve because the y values are bigger. And the reverse will happen. So when it's below 1, the new curve should be below the old curve. Now the negatives, again, you've got a bit of an issue because it's going to reflect over. Well, 1 squared is 1, so that's a good one to plot in. Negative 1 squared is 1 as well. So we'll plot that one in. And now I can draw it. Right? So here, below 1, so the new curve is below the old curve. We cross at 1, and now the new curve is above the old one because we've gone above 1. But that same idea for each of these. We're going below, above, and so on. We also know we have to bend towards the asymptote. So after we come through this one, we must bend and go asymptotic to the horizontal asymptote there. Ooh, and there it is in all its glory. Isn't that lovely? Okay, division. Again, just like I did with subtraction where I said, no, I'm thinking of subtraction as adding the negative. I can do a similar thing with multiplication. So I'm saying, well, yeah, okay, I'm dividing by g, but what I'm really doing is multiplying function x by its reciprocal of gx. And so then all the same procedures can be followed, except now the x-intercepts of gx will become vertical asymptotes because they're now on the bottom of the fraction. And so they can't equal 0. So we know they're going to be, or maybe point discontinuities. But we certainly know it's not going to be in the domain. So let's do this one. X plus 1, x minus 2, on x plus 2, x minus 1. And yes, the other day we saw a different way of doing this, where remember we did polynomial division and got all that information. So here's just another way we could approach the problem. Okay, well I'll have x-intercepts for the top of the fraction. So they're at negative 1 and 2. Bottom of the fraction will become vertical asymptotes. Can't have 0 on the bottom of the fraction. Now that's broken it up into regions. So the first one goes negative times negative times negative times negative, which is positive, and so on and so on. So I know the curve's going to be in all those regions. I can work out the y-intercept by just subbing in x equals 0. So I know y will equal 1. Now, what's happening? Again, you got that idea of dominance that might come into play. Or no, in this case, we've got 4 straight lines, so nothing's really going to dominate there. Find any asymptotes. So again, we could do our polynomial division like we did before. And we say, oh look, there's a horizontal asymptote at 1. So draw that one in. Is that enough information to draw our graph? Voila. So we're going to stay in this section up here, because we've got to bend towards the asymptotes. Haven't got any x-intercepts down here, so I can't cross over. But I know here I've got to go through this one. So I must start down the bottom, come up through the asymptote, go up, and then bend towards the other asymptote. And then on the right-hand side, we must have this sort of hyperbolic shape. And I think this is the last one, but it's an interesting one. Sine x divided by x. Well, there's y equals x. And there's y equals sine x. So we're going to divide sine x by x. So all of those x-intercepts are x-intercepts, but of course at 0, it's not going to be an x-intercept. This one will actually be a point discontinuity. This limit, which we haven't really looked at yet, it's what's known as the small angle theorem. For very small values of x, the sine of the angle is equal to the angle. You don't believe it, try in your calculator. Go sine and put in a really small number, and you'll find that answer is very close to that small number. So we know that as we're approaching 0, sine x on x will be close to 1. So I'm actually going to have a point discontinuity at 1. Shade in the regions, it's still got that going up and down shape. But think about it logically, what are we doing? We're getting sine x and we're dividing it by bigger and bigger and bigger numbers. So this time, when we wind along the x-axis, it's going to get smaller and smaller and smaller. So we get something like that. So as a wind, I might have exaggerated it a bit, but it gets a bit smaller as we go along. And goes up to the point discontinuity there. We end up with an even function. How do I know that? Because sine x is an odd function, x is an odd function, and odd times odd will always give you an even function. Basically, if you've got the same type of function, multiply them together, you end up with an even function. Here we go, I think I put it in, didn't I? Symmetry, yeah. So odd times odd will give you even times even will give you even. Different types of functions, they give you an odd function. Okay,